geometry. Tell them it's measurements and process. Oh, no, wait, hang on. It is analytical techniques, yeah. Hi! Welcome, everyone. Does the video work?
Yeah.
Post on the chat if the video works. Does the audio work? Yay! Woo-ha. Okay. You don't know how much effort's been put into this whole tech side of life. Cool. Okay. I'm going to give people a couple more minutes to join. So I want you to post your favorite chemistry jokes. They have to be chemistry. We'll do bio next week so you can get prepared for next week. But today has to be chem. So I was told one to remember that cations are always positive. So cations are always positive, which is a pretty abysmal joke, but it helped me. More like chem is, oh, that's a sad one. Is formic acid and antacid? I like that one, Emma. Mystery. Oh, I like that one. That makes me sound very smart. I'm unraveling a mystery. Oh, is the voice being repeated for everyone? No. Miriam, I think that might just be you. Maybe try and reload the page. Positive cat eyes. I like that one. I like this chat. It seems like we have good chemistry. Yes, Talia, that one makes me very happy. Okay, cool. Well, that's a good start. Basically, as my colleague said, if you've got any questions as I'm going along or anything comes up, just post it on this chat. And basically, we've got someone on it all the time, so they'll be able to put questions on a board because I can't see the chat once I start teaching. So post away. Let's get going. What did the teachers say when magnesium combined with OMG? Oh, that's good. That one's a good one. If you've got any tech problems, the only thing I can recommend is reloading the page. And do it on Chrome, yeah. Safari doesn't work. It's a bit of a picky software. This video, so basically what's going to happen is I've got a PowerPoint presentation. I'll make notes. After this, you'll be able to fill in a survey. And then if you fill in the survey, I'll send you all the notes. So you don't have to make any copious ones now. And you should be able to rewatch the film on this link as well. So if you don't get rid of this link, that should be fine. Okay, cool. I'm going to try to share my screen now, if it decides to go. My computer's a little slow today. Just bear with me. Okay, you should be able to see my PowerPoint pretty soon. Should be coming up. It says it's sharing. Is it sharing?
No.
Nope. Okay. Let me try that again. Okay. Right. Second attempt. Dia, you got a reaction from me with that joke, so don't worry. Clearly didn't feel too bad. Oh. No. Hang on. I think it's just having a tough time because, excitingly, there are 148 of you connected and it is dying slightly. Right, let's try again. Please work. Come on. Don't leave me hanging. It says it's sharing, but it's not going through. No. Oh, this isn't sharing. Sorry guys, bear with me. I'm a chemist, not a tech person.
Do you remember how we did it on the start?
I'm doing it the same way.
Okay.
It's just like struggling. I think it's because there are so many people on.
Let's see if Dan can help us out. Hi guys, finally.
You can though. It's just because it says it's sharing.
I'm sure it's right.
Keep posting jokes. Thanks for the sympathy with the lack. Oh, come on, Crowdcast. Don't do this. If not, I might do it. I might have to try on my laptop. Okay, come on. Okay, well, keep the jokes coming. Come at me. If you get organic chemistry jokes, you get extra points for those whilst we wait. Keep posting any urgent questions you might have. Huh? Yeah, no, you can't. No. It's not. It's Crowdcast that's struggling. Could we watch the video? Why are you? It appears as though you already died. Camera mic access. No, I didn't. Can you still see me?
Yeah.
Okay, go away. Okay, you know what? I'm going to switch my camera off, and maybe that'll help. Okay. Come on, Crowdcast, work with me. By the way, a special shout out to anyone who's my student, either OPT or winter courses. I'm excited to have you back. Oh my God, even my camera won't go away now.
Oh, it's on.
Okay, camera's gone away. Nope, it's back on. Okay. Oh my God. Okay, everything's just going a little slow. So we're just going to be patient. Camera should go away soon. There we go. I feel maybe if I patronize it, it'll work. Okay. Please share my screen. No. Oh, why? This is very irritating. It's not sharing or doing anything, is it?
Can't hear you.
Yeah, great. So I can teach you with no props. It keeps telling me to check my camera and my mic. Everyone can hear me. That is not the problem. Oh.
Oh, you're there.
Oh, okay. We are now on my laptop. Let's see if this works. Okay. Let me just get my.
Welcome back.
Thank you. You wouldn't imagine that we've actually spent quite some time preparing this and ensuring it worked. But hey. Okay. Let me just get this all set up. Okay, second try. Let's. I can't hear anything. Can you hear everything?
Yeah.
Okay. Jed, you might want to reload your page. Oh my gosh, I should have. It's not letting me share my screens now. Come on, Crowdcast, work with me. No, it's not letting me now install the screen share, so now I can't screen share. Can you sort your computers? Yeah. So I just had to click here, and it went to a page before, and it installed it.
Yeah.
But it's now not installing it.
Let me see.
Go have some potatoes. I don't think there's much you can do. It's just not installing the screen share, and that thing just died, basically. I'm on live, yeah. No, not that I know of.
We can do it.
Am I on again?
Yeah.
Install.
Great.
It's still saying
Oh, it's still not working. Add it to Chrome.
The only thing I suggest you should restart and refresh the screen.
Oh, yes.
Take it out.
Open PowerPoint and you don't matter.
Yeah. There we go. Oh, great. Okay. Oh, please. Can you see my screen?
Yes.
Oh, this is so difficult. It shouldn't have been this difficult. Okay, I'm now going to switch off my camera so you can just see the screen. I am so sorry to everyone. Okay, right. Let's get on with actual chemistry. Okay, so if I put it full screen, can you still see my screen?
Yes.
Okay,
yes.
great.
Oh,
Okay.
No. Oh,
You can't see my screen?
I can see it, but not full screen.
What do you mean? Turn your computer on. No, I've changed it. I'm on here now. Oh, fine. Fine? Okay. Can you now? Okay.
You just leave it like that.
Yeah, I'm just gonna leave it like this. Okay, so really quickly, basically, this is me. You've already seen me pull all kinds of faces trying to get this technology to work. Technology does not like me. I've been a tutor with Lantana for 4 years now, mostly doing chemistry, but I've done some bio as well. This beautiful meme here is because I did my master's in chemistry at Cambridge. I graduated last June. So that's my academic background. And this one's just because it's funny, because it's really nerdy. And I'm a nerd, but that's a good thing. Okay, so I thought really quickly, before we start doing all the organic chemistry stuff, we just have a look at the core exam format, because some people just get very confused. It's not going to suck away most of the time. We will get on the tuition, so don't worry. But basically, for higher level students, you're going to get your 1 hour multiple choice question paper. The way I would tackle this paper is basically when you're practicing, just assume you've got a minute a question. Now, some questions like your periodicity questions are going to take much less time than a minute. Other questions like quantitative chemistry, which is kind of the mathsy stuff, is going to take much more than a minute, but that's fine. And it'll just even itself out. Crucial thing here is just remember there's no negative marking whatsoever. So if you get really stuck, if you're getting really panicked in the exam, just circle anything and move on. It's not worth leaving it blank, basically. Remember, you can't do calculators. So for those of you who are lazy, and I know I definitely was lazy when I was doing the IB, make sure you can do all the mathsy questions in your head, or you've got your mental maths up to scratch, basically. No calculators whatever. You will get given a periodic table though. Some things are really, really good to know from the data booklet. Things like your gas constant, so 8.31, the heat capacity of water, 4.18. Those numbers seem really, really random, but when you're doing paper 1, they'll be super helpful. It's just, yeah, and they'll just mean that you go quicker throughout the exam as well. Then you've got paper 2, so this is 2 hours and 15 minutes. You've got the reading time included in that. These are short and long answer questions. You don't have the choices that you used to have in the old syllabus. So basically, you can't really hide. So whereas before I really hated acids and bases, so I just avoided those questions. But now you you have to do them. So you have to make sure you're okay with everything and you can face everything, basically. And here you can have calculators and you do have a data booklet. And then obviously the last paper is paper 3. So your first section is one on experimental data. Unfortunately, there isn't much practice on this. It is very new to the syllabus. There are a couple experimental questions that came up before, but it's a very different format. So sadly, there isn't much practice out there for that kind of for section A. The only thing I can say, comforting thing, is remember all students are in your position. So if you're stuck on section A and if you don't have much practice, they won't either. So don't panic. And section B is then obviously on your option. The options vary a lot. I wouldn't say there's particularly one that's easier than the other. I think each one has its own merits and its own difficulties. But I would say, I mean, it all depends on your school. My school would just choose my option for me. I never had a choice. But if you have a choice, obviously just go for one that you actually find interesting, because it is a fair bit of material. It does have a fair bit of weighting. If you think half this paper is just your option, that's 12% of your chemistry grade is just on the option. So it's worth really knowing that well. And then you are allowed calculators and data booklets. For standard level, it's very, very similar. And all the exams are obviously shorter. Paper 1, again, multiple choice questions. My advice is very much the same. If you're stuck, just circle something and move on. Not allowed calculators still. So again, work on your mental maths. If you ever get really, really panicked on a paper 1 question, I know I used to hate the first question because it's always on moles and it's always about number of atoms and this number of moles. And that was just, yeah, it was basically my nightmare. I don't know why, I just never understood that topic. So I usually would just skip it. And then once I'm just calmer and more in the swing of the exam, then I would just face it and deal with it as best I could. To this day, I still think I got that question wrong. I don't think it's something that I really understood aged 18. But hey, I still did fine and you can still do fine as well. And then paper 2 is very similar to the high level. So you've got short answer and long answer questions. Again, you've got limited choice, and you can use your calculators and data booklets. The main difference is that it is worth more than it's worth at high level. So do make sure you get a lot of paper 2 practice in there. I think what you'll realize with IB in general is the more practice you get, the easier it becomes, simply because they're quite limited in the number of questions they can ask you. So the more practice papers you do, basically the higher the chance you'll have seen whatever questions they throw at you in the exam. So I'd highly recommend doing that. And then just like with high level, you've got your option paper. Again, very, very similar advice. Section A, there isn't much out there for you to practice on. So I think that's a case of harassing your teachers to come up with questions. I'm not sure if there might be some of the new textbooks out there might have a lot of questions there because they're aware that no one has any practice. But basically it'll be general stuff that you can do anyway, like reading data, interpreting data, plotting graphs, that kind of thing, drawing conclusions. So it's just those skills that you develop throughout the year anyway. And then your section B again is on your option. Again, if you get any kind of choice, pick one that you find interesting. You will end up spending a fair bit of time learning it, so might as well. And again, calculators and data booklets are allowed. Cool, okay, so that's really briefly just the structure of your exam, so everyone's clear. I thought the next thing we could do is, because in all honesty, it's unlikely we'll run another chemistry workshop because it's so close to exams now and we've got to do biology, maths and physics. I thought I'd run through the topics and I would basically tell you guys what, considering I've tutored 5 years now, what I think really stands out and tends to come up a lot and what the IB likes to ask. So at least you can tailor your revision with kind of more of an aim. And I can tell you I've done a lot of exam papers. Cool, okay, so topic 1 is quantitative chemistry or stoichiometric chemistry. So this is all the mathsy stuff about moles. I'd say the most important thing is limiting and excess reagents. IB love to catch you out on this. At standard level, they tend to be a little bit nicer and they tend to actually tell you that there's a limiting and there's an excess reagent. At high level, the biggest tip I can give you is that they might not outrightly ask you to find the limiting and the excess. What they'll do is they'll give you masses for the starting materials, and that's your clue. So you really need to be on your guard. If you get masses for the 2 starting materials in the equation, that means figure out your limiting first and then do the rest of the calculation. Standard level, as I said, they tend to be nicer. The other thing is, remember the difference between your empirical and molecular formulae. So your empirical formula is the simplest ratio, but the molecule won't necessarily exist as that simplest ratio molecule, whereas the molecular ratio is the actual ratio in the molecule. And you'll have to calculate that from either the mass composition or percentage composition, that kind of thing. Concept of the mole, you'll get maybe 1 or 2 questions, not a big thing. Ideal gas laws, again, small thing, so not something to stress about. Topic 2 in general isn't red at all. By the way, my color scheme, red means it comes up a lot, and italics means it's high level. So topic 2 is a really, really small topic. You should be able to revise it quite quickly. And because it's so small, it just doesn't come up very often at all. I'd say the biggest thing here is the emission spectra. So really understand why the emission spectra shows that electrons live in shells. Just from a chemistry point of view, that's just quite a groundbreaking discovery they did there from quite literally some colored lines on a graph. But aside from that, I really wouldn't spend that much time on topic 2. It's not worth it. Paper 1 questions, there aren't that many of them. And paper 2, there are even fewer. They might sneak a couple in, like where you have to calculate the relative atomic mass, but I'd say that's pretty much about it. Cool. Topic 3, periodicity. So this is probably quite a dull topic in all honesty. It doesn't require that much understanding. The crux of this topic is just when electrons are further away from the nucleus, there are more shells, so there's more shielding. And so basically what that means is that then the electrons aren't held in as tightly. And that will have effects on radius, on electronegativity, reactivity, everything. So that's basically the basis for everything. The important thing with periodicity is to know all your patterns, but also just to be able to explain them. And in the exam, some people just tend to waffle. A lot of students waffle and they think, oh, the more I write, the higher the chance I'll get the score. in reality, I would recommend that you just write them in bullet points. The examiners won't mind. You're never marked down for writing in bullet points, and it'll just mean you're much more succinct, and you're not having, yeah, you're not gonna waffle basically, and so you're more likely to get the marks. Transition metals for you guys out there who are high level, I would say those are really the important part. Yes, you'll be asked on the trends, especially in paper 1. They'll be like, okay, it's moving across period 3. What's the most acidic? I don't know, oxide or chloride or whatever. But your transition metals are super important because it's very different. It's very difficult. They form colored complexes. The reason they form colored complexes is because the d orbitals are splitting in energy, and it's kind of the first time you've ever encountered that. So I would highly recommend making sure you know your transition metals inside out and the reasons why they form all these colored things, basically. Okay, topic 4. Title is in red because it is, I would say, the most important topic on the entire chemistry syllabus. It's a very core, basic topic, which means it comes up a lot in exam questions. It sneaks up everywhere. So you might have an exam question that starts off with a bit of organic, then goes into some bonding, then maybe goes into some quantitative. But bonding always tends to be mixed up in there. And the important type of bonding out of all of them is by far covalent bonding. So you really, really, really need to be comfortable drawing Lewis structures. Remember, you've always got to put in the electrons, you've got to put in the charges. Remember, most atoms just want to form a full shell with 8 electrons. So I really recommend that. In terms of intermolecular forces, one trick here is if you ever have a question on boiling points and melting points, always think of your intermolecular forces. So does it have London dispersion, dipole, or hydrogen bonds? Because basically the sneaky way of the IB asking you about intermolecular forces is asking about boiling points and melting points. They won't necessarily outrightly ask you about the intermolecular forces of a molecule. Allotropes of carbon, tiny, tiny topic. I mean, remember it for paper 1, but not much else outside of that. And then for the higher levels, hybridization tends to instill fear in people, unnecessarily so, in all honesty. All you need to remember is the definition. So it's all about the mixing of orbitals to make hybrid orbitals. Now, the reason we do it is purely a model. So we know that molecules form, say, a tetrahedral shape. If we take methane, it forms tetrahedral shape. And we know it uses the s orbital and the p orbitals. But basically, if you put the s and the p's together, it doesn't make a tetrahedral shape. And so that's why we hybridize everything, so they're all sp3 orbitals. I'm not going to go into detail, but all you need to know for hybridization is a definition, and you need to be able to work out sp, sp3, sp2. So someone wants some diagrams for hybridization, but yeah, this is a current problem, sadly, because I'm on my laptop. I can't draw anything. I wouldn't say you need to draw diagrams for hybridization, okay? So the way I remember it is, let's say you've got ethene. So ethene is 2 carbons with a double bond in between them. So if you look at each individual carbon, it's bonded to 1 other carbon and 2 hydrogens. So it's bonded to 3 atoms in total, which means you have to mix 3 orbitals. So you're going to mix 1s, you always mix 1s, and you only need 2 more orbitals, so you'll mix 2 p's. And so in ethene, your carbons are sp2. If you go to ethyne, which is 2 carbons with a triple bond between them instead, each bonded to hydrogen, if you look at each individual carbon, it's bonded to 1 carbon and 1 hydrogen. So it's bonded to 2 atoms, which means it needs 1s, and then it just needs 1 more orbital, which is the p. And so there it's sp. And lastly, if you look at ethane, so the alkane, where everything's just single bonds, each carbon is bonded to 3 hydrogens and 1 other carbon. So it's bonded to 4 atoms. So they all mix 1s and 3 p's. So basically, all you're really looking at is how many atoms is this carbon bonded to. That's how many orbitals you need. You're always going to have 1s, and you just add the extra p's, basically. to make up the number of atoms it's bonded to. Hang on, another question is being written up in terms of hybridization. Does dsp3, as in with d orbitals? No. You only need to know sp, sp2, and sp3. Once you start mixing the d's, it gets super complicated. And they're realistically only really going to ask you the hybridization of carbon, which means the highest hybridization is sp3 anyway, because it can only form 4 bonds, so it can only mix 1 s and 3 p's to make 4. So don't worry about d orbitals at all. Okay, any last minute questions on hybridization before I move on? Post now or be silent forever. Oh, the suspense is killing me. Okay. Well, if you've got more questions, ask away and I will answer as I go along. Trickiest thing of bonding, for sure, is hybridization. So if it's something you struggle with, just do definition and just learn how to figure out sp, sp2, and sp3. All you need to know, don't worry about actually understanding what it is if you don't have the time. It is not your priority. If you want to be a chemist, you can learn it later. Cool, okay. Topics 5, 6, and 7. So this is kind of thermodynamics and equilibrium and some kinetics as well. So topic 5, in terms of Hess cycles, so the first thing you've got to do is calculate enthalpy change. This is both standard and high level. In terms of Hess cycles, you rarely actually have to draw the cycle. So if you have a method where you just flip equations, just use that method. It's foolproof, it's fairly easy, you're not going to get it wrong. Bond enthalpies and calorimetry tend to fill people with less fear, so it should be fine. Entropy is quite straightforward. You just have to always remember the definition. So remember, entropy is a measure of disorder. So basically, the more positive an entropy is, the more disorder is present. And spontaneity just basically links together entropy and enthalpy. There, the only thing you really need to learn is your Gibbs free energy equation. So delta G equals delta H minus T delta S. Things to point out there, remember this equation, memorize it, don't rely on your data booklet because you'll have to use it in paper 1. The other thing is your units. So Gibbs energy, delta G, is always in kilojoules per mole. Enthalpy is in kilojoules per mole, but entropy tends to be in joules per Kelvin per mole. So you always need to remember to change entropy into kilojoules. The last thing is your Born-Haber cycles. Again, this is like hybridization, tends to fill students with fear. I don't blame you, I hated it when I did it. The only thing I can really suggest is to do it stepwise. So basically you always, you always atomize everything first. So make everything into gas and make it all individual molecules. Then you ionize it. So first ionization, then second if you need it, and third if you need that. Then you do electron affinity, so that's when the other atom is then gaining those electrons. And then you do your lattice enthalpies. And that's how you create a cycle. And you connect it with enthalpy of formation. I know this is all hard to visualize with no diagram, but I'm just trying to give you as many tips as I can in this hour to help you with your revision. Okay, kinetics tends to be fairly straightforward, really doesn't come up at all, much at all. For standard level, it's literally just what is collision theory, what is a rate of reaction, and what are the factors that affect the rate. So the factors, remember, are temperature, surface area, concentration, pressure, and a catalyst. I remember with Tesco PCAT, if that helps anyone, a bit of a wacky way that my teacher showed me. For higher levels, it then gets a bit tricky, calculating orders of reaction from experimental data. That could crop up in your paper 3 as potentially an experiment. Arrhenius equation is the other thing. Like your Gibbs energy, do memorize the Arrhenius equation. Don't just count on your data booklet. What was I gonna say? Oh yeah, and when you're plotting the graph, always remember your line has to have a negative gradient, always. Okay, and then the last thing is topic 7. This one's tiny, this one really doesn't come up much. For standard levels, just make sure you know Le Chatelier's pretty well. So if I change something to the equilibrium, it's gonna go one way or another. For high levels, I would really focus on equilibrium calculations because they're the tricky ones that can catch people out. I use the ICE method, which is basically where you calculate the initial, the equilibrium and the change in between. If you have another method, go for it. It works just as well. Cool, okay. Then topic 8, acids and bases. Another one, from now on, basically people don't like topics, is what I've gathered. I hated acids and bases. I absolutely hated the calculations, but you don't know how important they are. Buffer solutions, especially at high level, tends to catch a lot of people out with the calculations. All options have buffer calculations in the high level. So there's no way you can get away from it. In all honesty, I think that almost definitely going to ask something about a buffer calculation in your paper 3. So I really make sure you're happy with them. My biggest recommendation for this is to go through a lot of past papers, because basically when I was preparing for the first time to tutor, I was really worried about tutoring these calculations because I wasn't very good. And all I did was a load of past paper questions, and you realize just how similar they are. And they literally just change a few numbers and that's it. So it's all about calculations. I would split it like this. I would learn how to do strong acid base calculations and what equations you need there. So like pH equals negative log of H plus. Then I would do the weak acids and bases, which brings in some equilibrium knowledge. And then I would do the buffer solutions afterwards and kind of tie everything together. As for the rest, fairly straightforward. I wouldn't really stress about it. This acid deposition thing is new, but it's just a lot of information. It's kind of all about acid rain and all that stuff. It's just memorizing. If you memorize it, you'll be fine. Next one is redox. Redox numbers are tough. Writing redox equations can also be tough. Again, just be methodical. If you've got a sucky teacher and you're really lost with redox, there must be resources online to help you, because redox numbers literally just have a certain number of rules, and that's it. And from then, writing equations also just have a certain number of rules, so it shouldn't be a problem. Winkler method is new. Now this, I think, will really crop up just because it is brand new. It involves some of your knowledge from topic 1, and yeah, it's not too difficult. It's just remembering all the equations, the order of the equations for the Winkler method. But it's I think that one's very much worth learning. And then you've obviously got your electrochemical and your voltaic cells. Out of those two, I'd say the voltaic is really, really important, especially if you're higher level, because it's got all this stuff about spontaneity, which will then link to topic 5. So the question could then either go from topic 5 to topic 9, or standard electrode potentials as well, which just requires a little bit more understanding, basically. So I'd say they're the really important ones out of that. Cool, and then we get to topic 10. In all honesty, the biggest things here are all the reaction mechanisms that you have to learn. You have to learn to be very comfortable with drawing arrows, what the arrows mean, especially at high level, and yeah, and just be comfortable with those equations, basically. Yeah, okay, questions are coming my way.
Okay, acids and bases.
Yeah.
Do you need to calculate the pH of salt?
You don't need to
Salt hydrolysis.
Okay, you don't need to calculate the pH of salt hydrolysis equations. Basically, salt hydrolysis is just, they'll give you a salt, so for example, NaCl, and you don't have to calculate the specific pH, you just have to say whether it's basic, acidic, or neutral. With an example like NaCl, the easiest way, I think, is to think, okay, how was NaCl made? So that was the reaction between sodium hydroxide, NaOH, and hydrochloric acid, HCl, will make NaCl and water. Sodium hydroxide is a strong base, hydrochloric acid is a strong acid. They're going to completely neutralize each other, so NaCl in this case would be neutral. That's all you have to do in terms of hydrolysis, salt hydrolysis.
Okay.
Cool, next question.
Is there an easy way to figure out the Winkler method?
I don't know of a particular.
You have to memorize all the equations for the Winkler method.
Yeah, I don't know a particular easy way to do the Winkler method. You do just need to memorize the equations. There are only 4 of them, I think. Last time I looked. So it's a pain in your butt, and I get that. But no, I wouldn't say anything easy.
What is Tesco PCAT for?
Okay, so Tesco PCAT, I did rush over it. Basically, in topic 6, when you're doing factors of rate of reaction, So the test code, actually, I can type this, which will be easier so you can read it. Okay, so TE is for temperature. Then you've got S is for surface area. Then CO is for concentration. And the P is for pressure. And the CAT is for catalyst. So test code PCAT. So you won't forget anything. But that's basically all there is to it. It's just to remind you of all the possible factors. Cool.
Good. We'll start with that.
Okay, cool. Okay, moving on to actual organic chemistry. So the plan for the lesson is going to be flexible now that I can't draw anymore, but we'll get there. So basically, I'm going to cover some standard level. Obviously, I mean, we're running late, so I'm going to run over anyway, but we don't have time to cover the entire topic. So we're going to start with the standard level stuff. High levels, you might groan and moan and be like, oh, this is the easy stuff. In all honesty, it's the basics, it's the fundamentals. If you don't have this down, you are buggered for all the later stuff. Can you hear me now? Okay. Yeah, so still need to know the basics. Okay, so what is organic chemistry? It is all about this special molecule, atom even, carbon. So organic chemistry is so important because all living things are made of carbon. So we have carbon in everything, in our peptide, in our proteins, in our lipids, everything is based on carbon. Some molecules like carbon dioxide or carbonate ions, those are inorganic. So it's good to know that not everything made of carbon is organic, but the vast majority is. And basically organic chemistry just deals with carbon-based molecules, and it brings into that other atoms, so nitrogen, sulfurs, halogens, but the backbone is always carbon. As soon as the backbone is something else, it's no longer organic chemistry. You're going more into inorganic. Inorganic basically encompasses everything else. But I mean, that goes to show how important carbon is, that it's basically half of chemistry is just carbon-based chemistry. Why is it so important? Out of interest, I don't know, in all honesty. It could have been on other planets. It's very feasible that instead of life forming on carbon, it could have been formed on silicon, because silicon has very similar bonding properties. It's slightly bigger, so it would have different reactivity, but it just so happens that on Earth, carbon is the most stable and beneficial one, basically. Okay, so moving on, because carbon is such a complicated topic, it's all classed into homologous series. And homologous series are basically just families, is the way to think about it. So we group carbon molecules into families to make their study easier for chemists in general. So I've got here a family in front of you, and this is for alcohols. Sorry. Okay, family of alcohols. So first thing to note is that your molecules are growing by a CH2. So the only difference between your methanol and your ethanol is this CH2. Okay, I'm going to type this up. So that's your first characteristic, is that molecules differ, or neighboring molecules better, differ by a CH2. Your second characteristic is that they've all got the same general formula. I don't actually off the top of my head know the alcohol one, which is embarrassing for an organic chemist, but hey ho, we're all human. Same general formula. Okay, the third one is that they will have very similar chemical properties. Now, you've got to remember that chemical properties are all down to the functional group. That's literally the only thing you're interested in. So when you're looking at the reactivity of propanol, you just simplify it down to, okay, it's an alcohol, it's got an OH, it's going to do the same reactions as any other alcohol is going to do. And the other one is it's got a trend in physical properties. So remember when we were talking back in topic 4 about intermolecular forces, whenever the IB asks you about melting and boiling point, that's all you have to think about, intermolecular forces. Now, in these molecules, you're going to have hydrogen bonds with your OHs. So obviously that's the most important intermolecular bond, but they've each just got one hydrogen bond. So that would suggest it's going to be the same physical property. But what's differing is that the carbon chain is getting bigger. So you go from 1, 2, 3, 4. Now, when carbon chains get bigger and the molecule gets bigger as a whole, you've got to remember that your London dispersion forces become stronger because they all depend on the number of electrons in the molecule. So the more electrons in the molecule, the stronger your London dispersion forces, and so the higher the boiling point. So that's why overall there's always this trend because your molecules are always increasing in size. And so your boiling point will always be increasing as well as you move along the family. So higher levels and standard levels. Paper 1, this comes up quite a lot. It'll say which one of these are the characteristics of homologous series. These are the 4 in a nutshell that you need to know. You'll never really have to explain them in great depth. It's literally just know the list. So if we then go through the actual homologous series, these are the main ones that you're going to encounter at the IB. They have actually added ethers, which I forgot to add to this table, but hey. So the first one, most basic, are your alkanes. So that's all carbon-carbon single bonds. Your names always end in A. Then you've got your alkenes. These are carbon-carbon double bonds. They end in -ene. Alkynes, triple bonds, end in I. And that's your basically the most boring ones there. And you're just interested in your alkanes and your alkenes. Those two are going to be the most important ones out of those 3. Then you've got alcohols, which we just looked at. They're also going to be important. You're going to look at those reactions. Carboxylic acids, the important thing to remember is that your carboxylic acid is when you've got a C double bond O at the end of a molecule, as opposed to an ester down here, which is when you've got a C double bond O in the middle of a molecule. One second. Cool. Okay, then we've got ketones and aldehydes. Again, people really confuse them. So ketones are where you've got a C double bond O in the middle of a molecule. So you have to have carbon atoms on either side of that carbon that's double bonded to the oxygen. Whereas aldehydes are when you've got a C double bond O group that's at the end of a molecule. So that carbon will have to be bonded to at least one hydrogen to put it on the end. Yeah, basically it has to be at the end of the molecule is the crux of that. And then you've got amides and amines. Again, people get confused there. Amines are just an NH2 group on a chain, on a carbon chain, whereas amides are when you've got a C double bond O next to a nitrogen. The nitrogen can be bonded to hydrogens or carbons, whatever. The important thing is that you've got C double bond O and then nitrogen. So again, don't confuse amides with amines. Nitriles are pretty easy. It's just a C triple bonded to a nitrogen. And your haloalkanes, also called halogenoalkanes, doesn't matter which, are just when you've got a halogen in the molecule. You've got to be very comfortable with all of these groups, no matter what your level in chemistry. And you have to be able to identify them very quickly and basically know the reactions that kind of convert one to another, that kind of thing. Okay, question time.
No, it was just how do you have any tips for how you can learn these by heart in a good way?
Okay, learning these by heart. Not really, sadly. It's not something that I would sit down and learn this table. Don't do that. It's not going to stick, and it's just going to be a pain in your butt, and you're going to hate it. In all honesty, it's something you will pick up the more organic chemistry you'll do. So as you revise organic chemistry, as you start doing past papers, just whenever you're faced with a molecule, anywhere in chemistry, any molecule, even if it's not asking you to, make sure you sit down and point out, okay, this has an alkane functional group, or it's got a ketone, it's an ester, blah, blah, blah. And the more you name these molecules and force yourself to name them, the better, basically. The quicker you'll learn them. Yeah.
I'm saying, copy and cut the table so you can mix and match.
Yeah, you could do that. You could cut this table up, mix and match it. You could make almost like a card flipping over. So you could also put like the name of the homologous series on one side of card, and on the other side you could put the functional group, and almost like, you know, one of those games where you turn the cards upside down to reveal the functional group. That might test your memory. It's a bit of a game, so it's more fun. It's more than anything, it is just practice. It is just seeing these over and over again. Yeah.
One person saying, if possible, could you do an explanation on nucleophilic electron? Is that coming up?
Nucleophilic substitution is coming up.
Yeah.
but I'm not touching alkenes. I don't have time. So electrophilic addition won't come up. Ester formation, okay. There isn't much to know for an ester formation. If I do this, are you still seeing my PowerPoint? I'm just trying to find a picture to show you.
Yeah.
Yeah, that's fine. Okay, so ester formations are basically just a reaction between a carboxylic acid and an alcohol. It's called a condensation reaction because you're producing water. So the important thing is actually, what's more tricky is that people really struggle to learn how to name esters rather than the reaction itself. So if I just, hang on, let me just insert a slide here. Okay, so, okay, this is your ester formation on a very basic level. You've got your carboxylic acid on the left, and you've got your alcohol here on the right, and you form this ester. It's a condensation reaction because you've also got this water forming. And the important thing is, in order to name it, what I do is I basically kind of split it down the middle between the carbonyl, so the C double bond O, and the oxygen. And anything bonded to this single oxygen goes first. So I've got 2 carbons, so that goes first as F, and then I add YL, ethyl. And then anything bonded to this C double bond O comes second. So 1, 2, 3, prop, and it always ends in anoate. Anything outside that in terms of esters, you just need to know their uses. So it tends to be in like food preservation, perfume, that kind of thing. You don't need to know much more than that. You don't need to draw any mechanisms or anything like this for esters. Okay, moving on. Moving on. Okay, cool. So we're going to quickly start with alkanes. So alkanes are basically the dullest molecules you have. Reason for this is that they've got single bonds, they're carbon-carbon single bonds and carbon-hydrogen single bonds, which are really, really stable, really, really strong. They're just not going to break. And the other thing is that they're non-polar. So in terms of reactivity, you always want polar things because that always makes things more reactive because the electrons end up wanting to go to one atom over the other. 2 things they do, complete and incomplete combustion. In terms of writing equations, always remember complete combustion is when it combines with oxygen, goes to carbon dioxide and water, whereas incomplete combustion, it'll go to carbon and carbon monoxide and water as your product. You'll rarely have to write an equation for incomplete, but for complete combustion, you're going to have to write that a lot. So just always remember those products. It's very, very important. And the other thing is your free radical substitution. Okay, free radical substitution. So before we start on the mechanism, we have to look at how a bond can break. Because basically there are only 2 ways a bond can break, and people usually don't really think about this, but it's quite important. Yeah, go for it.
What's the difference between non-polar bonds and non-polar molecules?
Okay, good question. So I've just had a question, non-polar, what's the difference between non-polar bonds and non-polar molecules? Okay, if you've got a molecule like, let's take carbon tetrafluoride. Let me just try and get this a picture so I can get this on the PowerPoint. So hopefully you all know that fluorine is the most electronegative atom on the periodic table. So what this means is that it will be the one that attracts electrons to itself within a bond. So let me just copy and paste somewhere. Because it's attracting those electrons to itself, it makes the bond polar. There we go. Sorry, I'm very bad at multitasking and explaining whilst doing something else. Cool, okay, so this is carbon tetrafluoride. So these bonds are going to be polar. All the electrons are going to want to move towards the fluorine, and they will. So you can imagine the electrons kind of being at the ends of these bonds. But because this shape is a tetrahedral shape, you should know that from topic 4, it basically means all the bonds are pointing out evenly around the carbon. So it means that yes, each bond is polar, but overall they kind of cancel each other out because they're all pointing away from the carbon equally around the carbon. So it means that this molecule overall won't be polar, but it's got polar bonds in it. And so, yeah, and they ask that a lot actually in paper 1. They'll say which one of these molecules has polar bonds but is non-polar overall, What you're looking for is a symmetrical shape, so something like tetrahedral or octahedral, where the bonds all cancel out. So they've all got the same polarity. The polarity is just basically nullified. It doesn't exist in the molecule overall, even though each individual bond is polar. So that's your answer to that question. Okay, cool. Moving on to free radical substitution. So as I was talking, there are two ways to break a bond, and you should be aware of what these two ways are. Heterolytic fission. Hetero basically means different. So your atoms are going to end up looking different at the end of the fission, of the breaking of the bond. So what happens here is that one atom takes both electrons. So in the first equation, your Y took both electrons, and the other atom doesn't take any. These are two electrons, the ones that are in the bond. Or they do it the other way as well, where X takes both electrons and Y doesn't take any. The point is they look different. So Y in the second equation, for example, has no electrons from the bond and is positive, whereas X has both of them and is negative. The important thing to note here is that the atom that will take the electrons is always the more electronegative one. So in equation 1, this is Y is more electronegative, so it's able to attract the electrons, whereas in equation 2, they've said X is. The other one, which is what we're interested in terms of free radical substitution, is homolytic fission. So homo means the same, so it's basically you're breaking the bond so the atoms look the same afterwards. And so what that means is that each atom will take one electron from the bond, and so they end up with one unpaired electron and no charge whatsoever, because they're basically just taking back their own electron that they put in the covalent bond in the first place. So that's why they're not positive or negative, they're still neutral. But they do have one unpaired electron. Now what this means is that it's incredibly unstable. I'm sure you've heard about all the awful health things that free radicals do in your body, because they collide with everything and they react with everything, basically. So these are really, really unstable and really reactive. And this is how this whole mechanism works, is just with these guys. So if we look at the actual mechanism, give me a sec to get another image. Okay. So sometimes the IB will ask you what particular reagents do you need to use for this reaction. The important ones here are UV light and UV light and more UV light. With no UV light, this thing doesn't work. Now what happens is you've got 4 stages, and you need to know all the names of the stages, and you need to be happy and comfortable with them. So first stage is initiation. This is basically where your chlorine is breaking up into 2 chlorine-free radicals. So this is a homolytic fission, and the reason why it breaks the chlorine-chlorine bonds is because they're weaker than the carbon-carbon and carbon-hydrogen bonds. So the way I would answer all these questions is always write a little spiel on what's happening, and then also write the equation. So basically exactly how it's written here. Once you've got those chlorine-free radicals, they're really reactive. So you get propagation, which is basically the chlorine-free radical will attack the alkane. Now, it's not going to react with the carbons, the alkane, because they're really shielded by the hydrogens. Instead, what it's going to do is it's just going to rip off one of those hydrogens. So you end up with a methyl free radical and with hydrochloric acid. Then this methyl free radical, again, is really, really reactive. Some of the chlorine atoms won't be broken by the UV light, so it'll react with that chlorine, rip off a chlorine, and that's how you get your haloalkane, and you'll get your chloride free radical as well. And basically this propagation just keeps on going until you get to a termination step. So, oh no, that's not what I wanted to do. What have I done? Let me get an image. I lost my image. Okay, here we go. So until you get to your termination stage. Now, termination is always when you have 2 free radicals combining. And that's, you can get different combinations of free radicals combining, but the point is still the same. It's always 2 free radicals. So you could get 2 chlorines coming back together. So you could get some chloride, just some normal chlorine reforming. You could get your CH3 and your Cl coming together, which is the product you want, this haloalkane. Or you could get 2 CH3s coming together, which is just a new alkane, a bigger alkane. So the point is, in terms of the IB, you need to know, okay, I'm mixing a halogen with an alkane, and I'm going to get a haloalkane and a hydrogen halide, so like hydrochloric acid. However, you'll have to be aware that you're also going to have a mixture of products. So you're going to have some bigger alkanes and just some chlorine left over as well. What do we do with that? We basically just purify it out, and that will get you your product. Anyway, that is the crux of free radical substitution. As I said, literally, you just need to remember these 4 stages: initiation, well, 3, initiation, propagation, and termination. The only variations they could do is give you a slightly different alkane or a different halogen. So, and the important thing to remember is that your halogen free radical will always rip off a hydrogen first, and then the halide, the alkyl free radical, so the CH3 free radical, will then react with the chlorine. Yeah.
What kind of questions are they asked regarding free radicals?
Okay, questions on this topic. It's a really good way to convert alkanes to haloalkanes. So sometimes they'll give you like a reaction. They'll say, how do I get from, I don't know, this homologous group to this homologous group? It's very, very good to know that alkanes can become haloalkanes like this. They'll also just ask you, ethane reacted with chlorine. What happened? And basically you just have to go through free radical substitution. So you just have to think, okay, ethane, that's an alkane. What do alkanes do? Combust and free radical. If you're reacting with chlorine, it's definitely not combusting. So it's got to be free radical. And so it's really straightforward, and you basically just have to go through this mechanism, or they'll give you bromine. So they'll give you chlorine or bromine. But fundamentally with free radical substitution, they're very limited with their questions. So they can just ask you to go through these 4 steps that I've written for you.
So what about free radical substitution with other elements, not C elements?
You only need to know free radical substitution in terms of alkanes when they react with chlorine and bromine. You don't need to know any other kind of free radical substitution. In all honesty, I don't think I've ever come across another kind of free radical substitution. Free radicals are just very unstable. They don't tend to form that much, which is why this reaction is just quite rare in general. Any other questions? Nope. Okay, cool. So as I mentioned, because we don't have all that much time, sadly, I skipped alkenes. For the standard level people, alkenes literally just memorize, if I add hydrogen, I get an alkane. If I add halide, I get a haloalkane. Test for bromine water, that kind of stuff. Polymerization. For the higher levels, I would focus more on electrophilic addition and Markov-Nikolson rule. Because that's new to the syllabus. Well, it's not new to the syllabus, but it's new to the core syllabus. So they're more likely to ask stuff. Yeah, but I would just focus on that stuff if you're high level. In terms of alcohols, so this is the last bit for the standard levels. Okay, so alcohols combust. So I've got a beautiful page here of combustion of alcohols. Again, remember, incomplete gives you carbon monoxide and water. Could also give you carbon gas. And complete is always with carbon dioxide and water. As I mentioned with alkenes, the products of complete combustion comes up a lot. It's one of those basic reactions that they'll always ask you. The other thing alcohols do is they get oxidized. Before we look at oxidation, it's important just to be able to classify alcohols. So methanol is kind of a bit of an exception to this classification, but if we look at the rest, primary alcohol is when you've got a carbon bonded to an OH, and that's bonded to one other carbon. So that's primary. Secondary is when the carbon bonded to the OH is bonded to 2 other carbons. And a tertiary is when a carbon bonded to OH is bonded to 3 other carbons. So really makes sense. It's for once scientists were very smart in naming them this way. And it makes life easier in terms of oxidation. So, oh yeah?
If we had to write down the equations for combustion of alcohol ourselves, how would we determine which alcohol would combust partially and completely?
Okay, so whenever you have to write equations for combustion of alcohols, they're only going to make you write equations for complete combustion, because incomplete is a nightmare because it doesn't always balance out. You will have some carbon in there as well.
whenever they mention combustion, you can basically always assume it's complete when you're writing down an equation. So you're always going to have to write it combining with oxygen and giving carbon dioxide and water. It's good to be aware that you get incomplete combustion as well, but it's not an equation that you're ever going to have to write out in the exam for that. Okay, on to our oxidation. So oxidation of alcohols, again, reagents. You're going to need heat, and you're going to need acidified potassium dichromate. It's important you mention it's acidified because that does change the whole reaction. And it's also important you know it goes from orange to green. You might have been given another one. I think it's potassium permanganate that can also do this. I'm not sure. But if your school gave you another one, there is another one out there. I just learned potassium dichromate, so that's the one I teach. Okay, and from there it's quite easy. So your primary alcohols, so this carbon that's bonded to one other carbon, with limiting oxidizing agent, so the O in brackets means oxidizing agent, which is this acidified potassium dichromate. If you've got a limiting amount of that, it will become an aldehyde. You'd also have to distill it. For those of you that don't know what distillation is, basically you just heat your primary alcohol, and as soon as it becomes an aldehyde, you filter it off. It's complicated apparatus. It doesn't really matter. You don't need to know much more than that. But basically, as soon as the aldehyde is made, it's taken away from the reaction. If you react the primary alcohol with excess oxidizing agent, so excess acidified potassium dichromate, you get a carboxylic acid. And this guy you have to put under reflux. Now, reflux is basically you heat it, the primary alcohol will boil, it'll evaporate, change into this carboxylic acid, and then condense back down and go back into the solution and then be reheated again. The reason it's in reflux is because not all the primary alcohol will go straight to the carboxylic acid. Some of it will go to the aldehyde. So the point is the aldehyde would then recondense again and be reheated again, and so then hopefully change all the way to the carboxylic acid. It's basically just a way of ensuring you only get the carboxylic acid. Secondary alcohols, they only do full oxidation with excess oxidizing agent and reflux to a ketone, and your tertiary alcohols don't do anything. So again, kinds of questions that come up on this is basically mostly in a reaction scheme. So they'll say, for higher level, for example, they might say an alkane goes to a carboxylic acid. How does it do this? Well, the alkane we've just learned can do free radical substitution. So it could become a haloalkane. The haloalkane will then undergo SN1 or SN2 and become an alcohol, and then the alcohol will be oxidized to a carboxylic acid. So those are the kind of things that come up. For standard level, it's much more obvious. So they'll say, this alcohol goes to a carboxylic acid, give the reagents, or if I put this alcohol with these reagents, what is my product? Those are the kinds of questions about standard level. Do you have a question?
Yeah. Can you just quickly explain reflux again?
Yep. Okay, 1 second. Let me actually just get a picture of reflux. Reflux, in all honesty, it's almost like when you get, the stomach reflux is basically it comes back up and then you swallow it back down, which is really gross. But that's basically all you're doing just in the lab. Let me find, okay. We're getting a full-on picture of the apparatus. Okay, so this is my reflux thing. So you're heating your solution in this beaker. As it heats up, it goes up this tube. And let's say we've got a primary alcohol, it's turned into an aldehyde. But we want to make it a carboxylic acid. We want it to fully react. So to ensure that, it'll go up this tube, and rather than leaving, it's then just going to condense again because we've got this water that makes this surface cold. So it'll condense back down and it'll go down into the beaker. It'll then heat up again, and this time it'll have enough energy and enough oxidizing agent, and it will then become the carboxylic acid. Carboxylic acid might also condense back down and go back in the beaker, but it can't react any further. So all reflux does is basically, it makes sure everything is fully reacted, so you only get your carboxylic acid as a product, rather than a mixture of carboxylic acid and aldehyde, which you don't want, because then you'd have to purify and it's just a bit of a mess. So this is all refluxes. The only situation I can see reflux actually coming up is with that experimental question in your third paper. Usually they don't actually ask for a definition of reflux in terms of alcohols. Does that make sense? No comment. Okay, cool. Hopefully that makes sense.
As one more question.
Yeah.
Could you expand on the conditions needed for fractional distillation, i.e. what temperature?
Oh, okay. Temperature-wise for distillation, really depends on what kind of alcohol you've got. If you've got a small alcohol, it's going to make a small aldehyde, so it's going to have a very low boiling point because those intermolecular forces are going to be weaker because it's just smaller. So you'll need a lower temperature. Whereas if you've got a bigger molecule, it'll have stronger London dispersion, higher boiling point, so you need a higher temperature. So there isn't like a one temperature fits all. And needless to say, you're not going to be asked for the temperature in the exam. Any other questions? No. Okay, cool. So before I lose the standard levels, I've just got a few questions here, which sadly won't work quite as well without my writing techniques, but hey, we'll just go through them quickly. It's for high levels as well. High levels will have these questions, so don't switch off. Okay, so the first one, how many alcohols have the general formula C4H10O? Now, the way I would do this is I would basically just draw out all the different alcohols. This could be very time consuming, so you got to do it in a clever way. And basically, I would do the 4 carbons in a row, then put the OH on the end, and you could also put it on carbon 2. So that gives me 2 ways. Then I could draw 3 in a row, 3 carbons in a row, with 1 carbon coming off the middle. And then again, there are 2 ways. You could put the alcohol coming off the end, off the end or the middle carbon. So the answer here is B. The important thing to take from here is just do things methodically. In the exam, you'll be panicked, you'll be stressed, you're bound to just, when you see this question, just start drawing molecules. So it's important that when you're doing practice papers, you always do a logical, you always use a logical route to answer these questions. Otherwise, you're going to waste too much time. General formula of alkynes. Now, the reason I've done this is because a lot of you might just draw the first alkyne. So that's 2 carbons with a triple bond in between and 2 H's. And you might think, oh, that's got 2 carbons, 2 hydrogens, it's CnHn, it's A. If you were to draw the next alkyne, which has 3 carbons, you'll actually find the formula is B. So basically, a lot of the other options in the exam. Okay, right. Okay, if I finish 24, so basically the important point is that the IB always put in sneaky questions where the other options are kind of basically traps for people. So do always think, okay, am I sure about this? Have I tried, various ones in the series, etc., etc. Okay, going back to question 23, the easiest way to explain this for any of you struggling to draw it is just to get them up. So the first one is going to be butan 1-ol. So that molecule looks like this guy. So this guy is butan 1-ol. That is option 1. The other option is if we then move this hydroxide and put it on carbon 2 over here. I'm not going to draw it because it's the same, but it's basically butan 2-ol. So that's 2 options. Then the third option is 2-methyl propan 1-ol. And that guy is going to look like, let me get it up, this. Okay. It's going to look like this guy. So that gives us 3 options. And the last option is if I then move that hydroxide and put it on this central carbon here instead of this hydrogen. So that would then be 2-methyl propan 2-ol rather than propan 1-ol. And so that's how you get your 4 options up here. Again, 3 catches a lot of people out. So it is smart to just think, okay, is there any way I could make 4 before we move on? Cool. 25 here is just a question on the alcohols. So which one can both be esterified and turn acidified potassium dichromate green? So the important thing here is the only thing that can turn it green is an alcohol. So it can only be A or C because it has to end in OH. It can't be A because if you draw out A, it's a tertiary alcohol, so it's got to be C.
It's just a bit difficult seeing the
Oh.
options. So do you want to either make it bigger or read them?
Is that clear? It's the numbers is
It's
really
the numbers,
poor.
yeah.
Yeah. Okay. So the first guy is 3 CH3s with a COH. So it's an alcohol, but it's a tertiary alcohol. The second guy is CH3, CH2, CO2H. So that's a carboxylic acid. So that's not going to react with potassium dichromate. Next one is CH3, 2 CH3s with a CHOH. So that's going to be a secondary alcohol. So that will react with potassium dichromate. And it can also be esterified if you react it with a carboxylic acid. And the last one is CH3, CH2, COCH3. So this is a C double bond O in the middle of the molecule. So that's a ketone. Whereas if it was at the end of the molecule, it would be an aldehyde. So also linking back to when we were discussing like how do you remember all these functional groups, you can very easily go down all these molecules and name all their functional groups. And that's good practice in itself. Even though it's not answering the question, it's just good practice beforehand. Okay, the last thing is reaction between ethane and chlorine. And
how do I calculate the general formula for an alkane for question from 4?
Oh, okay.
Sorry.
No, it's fine. Okay, for an alkyne, calculating the general formula. Sorry to be going backwards and forwards. The questions are just slightly out of sync. What you have to do is, and the easiest way, the way I did it, was I just drawed the first two alkynes. So if I get that up. So the first one is just ethyne. And that one looks like this guy, which is coming on screen in just a second. This guy, ooh, a little bit big. So the misleading thing is that in the exam, if you only draw this one, you'll think it's option A. Option A is CNHN, because at the moment you've got 2 carbons and 2 hydrogens. So that's why I'd always recommend that you draw the first 2 to make sure that you've exhausted your options, basically. First 2 should be enough. If you really want to be safe, do the first 3. So the second one, as I'm sure most of you know, is propyne. So that's when you've got 3 carbons in there. And that one looks like this guy. And this guy you'll see isn't CNHN, because otherwise you'd have 3 carbons and 3 hydrogens. You've got 3 carbons and 4 hydrogens. So then I'd look at the next one, B, which is CnH2n minus 2, and that fits both of these. So I'd say, yep, that looks right. CnH2n doesn't fit 1 to begin with, and CnH2n plus 2 doesn't fit 1 either. So that's how I would do it. If you're good at memorizing, you could also just memorize the general formula. In all honesty, you have plenty to memorize, so it's a bit of a waste of brain space. Okay, so that's 24. Last one here, 26. Which mechanism reaction between ethane and chlorine in sunlight? Sunlight, remember, is a source of UV. Ethane's an alkane, so it can only combust or do free radical substitution. So it's just got to be A. You don't have free radical addition anywhere in the syllabus. You don't have electrophilic substitution either. But you do have electrophilic addition, which is in alkenes. So just make sure you really keep these concepts separate in your head so you don't get confused with these questions. Okay, another 3 questions. Which is not a possible product when propane reacts with chlorine? Again, this is just looking at free radical substitution. So usually our product is C, C3H7Cl, because that's just when the alkane becomes a haloalkane. But remember, some Cl2 will be left unreacted, so that is a potential product. B, you can't read it, but it's basically just 2 propanes coming together, which again, remember, it's a possibility, because if you've got 2 propyl free radicals, they will just combine and make that molecule. So it's got to be A. Features of successive homologous series. This is just learning. We said it's similar chemical properties, same general formula, differed by CH2. So it's all 3 in D. And the last one, this alcohol can be oxidized under reflux. deduce the structural formula of the final product. So the important thing is, first ask yourself, is it primary, secondary, or tertiary? This guy is primary because the carbon with the OH is bonded to one other carbon. And it's heated under reflux. So it's going to go all the way and it's going to form a carboxylic acid. The color change is always orange to green.
So we're just asking if the answer was for propane.
For what? Which one?
The propane one.
Propane question. This 27. Whoever's asking the question, 27.
27. 27.
Yes. Okay. The answer was A. You never ever make hydrogen when you react propane with chlorine. Yeah, because B you get when you get two of these propane molecules combining as free radicals. C you get when the propane combines with the chlorine, and chlorine is just, sometimes it's just unreacted. So hydrogen is the only one you'll never produce. All good? Any questions? Okay. Oh, fantastic. Glad you got it. Okay, this is where I say goodbye to standard levels because I'm just going to quickly go over nucleophilic substitution for those of you who wanted it.
I do not want one question.
Okay, hit me with the question.
Why would you never produce
Okay, why would you never produce hydrogen? Because you either have a haloalkane, a halogen free radical combining with a hydrogen. So that's always going to be an HCl or an HBr. Or you'll have an alcohol free radical combining with a halogen. So that'll form your like CH3Cl. You're never going to have a hydrogen free radical reacting with another hydrogen, fundamentally just because hydrogen free radicals are far too reactive. It's just too unstable. So it's incredibly unfavorable for it to form. So it's just never going to form a free radical. So you're never going to get the reaction that would make hydrogen in this scenario, if that makes sense, which hopefully does. Cool, okay. So nucleophilic substitution, we're just going to breeze through this because I realize it has now been an hour and a half. Okay, fundamentally, you've got primary, secondary, tertiary haloalkanes. So nucleophilic substitution is all about haloalkanes, which I'll just write here. Again, definition is very similar to the alcohol. So primary one is where the carbon with a haloalkane, which is this X, is bonded to one other carbon. Secondary is when it's bonded to 2, and tertiary is when it's bonded to 3. So whenever you're faced with an alcohol question or a nucleophilic substitution question, always split it in terms of its haloalkane, in terms of primary, secondary, and tertiary. And that'll just get the ball rolling in the correct direction. The other thing to be aware of is you can have various nucleophiles. Now, at a base level, a nucleophile is something that loves nucleons, or the nucleus, basically. So it's something that's got an extra pair of electrons that it can give away. Substitution is a given. You're basically substituting your halogen by something else, by your nucleophile. Examples of nucleophiles, they can be negative or they can be neutral. Negative ones, main ones are hydroxide ions or cyanide ions. There's one more that I've forgotten. Neutral ones, things like water or ammonia are your main ones. The one I'm going to focus on today is hydroxide just because it's the most interesting and it's the most fun. Okay, so the first one is SN2. Now, SN2 happens with your primary halo. Can you hear me now? Yeah? Okay, I just put my hand on it. Let me try to find this. Okay, here we go. So it's always with your primary haloalkanes, as I said, and that's why I'm teaching it first. Now, SN2, S stands for substitution, N for nucleophilic, and 2 means bimolecular. Bimolecular links into rates of reaction. So it basically means you've got 2 molecules in your rate determining step. So if we look at the mechanism, these arrows you will have to learn to draw. So let's say your nucleophile is an OH minus, and it attacks your carbon with the chlorine. Because it's transferring 2 electrons, remember these arrows each show movement of pairs of electrons. this will then kick off your chlorine, and your chlorine then like goes swimming away happily. Then you go into this transition state. Transition state will mean that the carbon is half bonded to the oxygen and half bonded to the chlorine. Now, the reason it's called a transition state is because this isn't something we can isolate or take away, but we know that the molecule has to go through this in order for the reaction to occur.
This is all HL.
This is all HL, yeah. So SL can go to it. Cool, and then you end up with this alcohol and Cl-. Now, the way I learn SN2, I can give you a suggestion, because it's quite good fun. I really like SN2 and SN1. Basically, think of it in terms of a relationship. So SN2 is basically when you've got, yeah?
Wait, how do we know that it goes through the transition state?
All SN2 reactions go through the transition state, always. And you will always have to draw the transition state, or the IB don't give you full marks. Yeah, so the way I remember this is in terms of relationship. So carbon and chlorine are in an unhappy relationship. In order to, I am going to stereotype, so I apologize. This could work both ways, but we're going to say carbon is a dude and is not one of the nice ones. So carbon and chlorine in this relationship, and they're kind of rocky. So then the HO comes along, it's OH minus, and carbon decides to get into a bit of a relationship with the HO. But at one point he's being a bit of a dick. He's still half in a relationship with chlorine, half in a relationship with the HO. And then he decides, you know what, HO's more fun. I'm going to stay with her. And they become an alcohol and they fully state their relationship. And chlorine goes off feeling pretty negative, so it's negatively charged because it's pretty sad. It's a bit of a bummer. Carbon wasn't very nice to her. But hey ho. As I said, gender stereotype, so you can switch that around and carbon can be a girl. But the HO works better when carbon's a man. So that's how I remember it. It's a little bit fun. You can do posters as well. You can teach your teddy bears, always helps. But it's good to just, in all honesty, just draw this mechanism out over and over again. The kinds of questions you'll get will literally just to be drawing this exact mechanism, and it'll be worth, say, 5 marks. And that's really easy 5 marks if you know how to draw it. Question? Nope, no question.
Okay, continue.
Question? No.
No, I accidentally closed it.
Okay, cool. Questions will wait till after SN2. So SN1 even. Actually, just before I do that, just as a reminder, SN2 is primary halalkanes. Cool. Oh, and the last thing is, the reason it's 2, as I said, bimolecular, 2 molecules in your rate determining step. In this first step, you've got the halalkane and you've got the HO. That's 2 molecules, hence SN2. And this first step is the rate determining step. Always is the rate determining step for SN2. Okay, SN1, let me find a picture for that. SN1 is for your tertiary halalkanes. And the reason this is that tertiary halalkanes are really, really bulky. So they basically can't undergo SN2 because SN2, your OH minus is attacking in at the carbon. The carbon in these tertiary halalkanes is too crowded. So your HO would never be able to get in there, basically. It gets stuck. So tertiary halalkanes undergo SN1.
I have a question. How do we know which molecules go through?
Okay, so if you've got a primary halalkane, so this guy with a carbon, halogen, and 1 other carbon, that's going to go through SN2. So this is the mechanism you're going to draw. If you've got a carbon bonded to 3 other carbons, also bonded to the halalkane, it's going to go to SN1. So this carbon with 3 carbons. So that's how you know. So the first thing is always to figure out, is it primary, secondary, or tertiary? Now this mechanism is SN1. 1 means you've got 1 molecule in your rate determining step. So that's this first step here is your slow step. You've only got your halalkane. What happens is your carbon-halogen bond breaks, and you get the nucleophile attacking in here, and you get your product. Now this step in the middle is not a transition state, it's an intermediate. The reason it's an intermediate is that, so the difference between intermediate and transition state is that an intermediate we can actually extract and we can test for it, whereas a transition state is just theoretical. We can't actually know for sure that that ever exists. And this is specifically a carbocation intermediate. Cation is positive, carbo because carbon is what's positive.
I have a question here.
Yeah.
Like, catch, right.
What
Is
is it?
biomolecular
So bimolecular, yeah, bimolecular means the order of reaction is 2 with respect to the reaction overall. It's order 1 with respect to HO and with respect to your haloalkane, but it's 2 overall. So yeah, 2 also works there. Yeah, next question.
in tertiary, isn't there steric hindrance? So that's why it has SN1.
Yes, so the steric hindrance is what I was talking about in terms of the fact that the OH minus nucleophile isn't able to tack into the carbon because these carbons block it. The fancy word for that is indeed steric hindrance. So always best to know that, especially at high level, because you'll get a lot of marks. If you can describe it though, that is just as good. You will get the marks if you describe steric hindrance. The other reason you get SN1 is because your carbocation is only stable, isn't stable with primary haloalkanes. The reason that is that basically this positive charge is almost kind of cancelled out by the higher number of carbons you've got around it. Now your primary haloalkane only has, well, this one doesn't have any carbons, but only has 1 carbon max. So the positive charge wouldn't be cancelled out, it wouldn't be stabilized enough. So that's the other reason why tertiary go by SN1 and primary go by SN2. The carbocation is just more stable when it's tertiary. Yes.
Wasn't there something to do with flipping the molecules for SN2?
Yeah, so for SN2, okay, for SN2, you will notice as well, you get these dashed and what they're called, block lines as bonds, and you'll see that the carbon, that they now point this way on the right, so they point towards the right on the right of the equation, whereas they point on the left to the left. Basically, you get an inversion at carbon with SN2. So that is a good thing to note. Not something that comes up very often, but usually in terms of questions, they're usually just more focused on the mechanism and just being able to draw that. Next question.
Okay, 2 more questions.
Yeah.
Well, yeah. What causes the halogen to break off the alkane in SN1?
Oh, interesting. Okay, so in SN1, it does seem a bit random that the halogen just breaks off. In all honesty, partly it will be this nucleophile. It will have an effect and it will be incentivizing the halogen to move off because it's more favorable to have this carbon nucleophile bond, just because it'll be stronger. Yeah, but the nucleophile itself doesn't attack until the space is free, is the important thing to remember. But it does have a way of helping the halogen leave. Can't say I've ever seen a question come up on that though. That's, I would say, probably beyond the IB.
What's the NUC?
NUC stands for nucleophile. So that would be like up here I have OH minus. You could put an OH minus with the NUC. You could put CN minus. It would all work.
So what's the difference between SN1 and SN2 apart from the primary tertiary?
Okay, so main differences between SN1 and SN2. Haloalkanes, obviously, primary do SN2, tertiary do SN1. Secondly, SN2 has 2 molecules in your rate determining step. SN1 only has 1. And the third one is you get a transition state in SN2, whereas you get a carbocation intermediate in SN1.
Okay, cool.
Any more? Okay, great. Okay, so those of you who are thinking will think, okay, you've talked about primary, you've talked about tertiary, what about secondary? Basically, secondary is the IB's way of being nice because it means you can pick either SN2 or SN1 to talk about. They both work with secondary. Why? Because they're not too sterically hindered, so they can undergo SN2 and they can undergo this inversion. That's fine. And the carbocation is slightly more stable, so it can form, so it can also undergo SN1. There's no right answer, basically. There's no right, there's no wrong answer. Basically, you just pick whichever one you're more comfortable with, and that's one you do for secondary haloalkanes. Last thing on this topic is factors affecting. Oh, yeah, one question.
Is steric hindrance the same thing as solvent shell?
Okay, so there's a question that is steric hindrance the same as a solvent shell? No, I would say they're marginally different. So steric hindrance is when you just look at the molecule itself. This carbon has 3 carbons around it, each with 3 hydrogens around them. So it's just going to be a bulky molecule as a whole. And they're going to provide a lot of steric hindrance, blocking anything from attacking it, basically. Whereas a solvent shell is when the solvent is involved. So when you're forming bonds to the surrounding solvent, which will add to steric hindrance, but I would never say they're the same thing. But it will definitely have an impact, and you can choose between these two, between SN1 and SN2, depending on solvent. And so it's important to know that it will play a role in that. Okay, the fundamentals of that is that basically protic solvents, which are polar, so water and ethanol, will always favor SN1 because basically they'll stabilize this carbocation, they'll stabilize the anion that leaves, so it's very stable. Whereas aprotic solvents, which are less polar, will always favor SN2 because they'll just favor this transition state. Because aprotic solvents are non-polar, they don't like ions in solution. This transition state takes up this OH minus ion. And so you basically have fewer ions in the solution, which is happier for the solvent. So solvent is important, but as I said, solvent shell, slightly different to steric hindrance. Anyway. Okay, cool. Last thing, and then we will all go. It's just factors that affect the rate of nucleophilic. Oh no, I didn't mean to do that. Affect the rate of nucleophilic substitution. So first factor is the nature of the nucleophile. So this is basically just something that you need to learn. Anions, oh yeah, this is kind of like a intuitive thing. If you've got a nucleophile that's negatively charged, it's going to be more reactive than something that's neutral. Something that's neutral is already quite stable, quite happy, it'll just sit there. Whereas something that is negatively charged, that's much more likely to react. So anions are more reactive nucleophiles than neutrally charged species. Okay, number 2 is the nature of the halogen. Oh, nature of the halogen. So in all of these reactions, you're breaking the carbon-halogen bond. So if that carbon-halogen bond is weaker, it's going to be easier to break. So weaker carbon-halogen bond means faster reaction. So that means that the reaction will be fastest with iodine, then bromine, and then chlorine, because your iodine bonds are weakest and your chlorine bonds are strongest. In fact, fluorine bonds are so strong that they don't react. So iodoalkanes react fastest as Ci bonds are weaker than CBr and CCl. And the last thing is the nature of the halalkane. So basically, if you've got a tertiary halalkane undergoing SN1, SN1 as a general route is faster than your SN2, just because in SN2 you form this transition state, it's very high in energy, so it's less likely to form. So the crux of this is SN1 is faster than SN2 because the transition state in SN2 is very high in energy, so difficult to form. Cool, and that is the crux of nucleophilic substitution in a nutshell, a very fast nutshell, granted. So, I hope that was helpful. That's basically all I've got left to say. Yeah, hit me.
Do we have to memorize examples?
You don't need to memorize example of halogenalkanes, but basically the important thing is that it is just anything with any carbon-hydrogen bond, basically. And so as long as you just, yeah, you're not going to have to ever memorize specific structures. They'll always give you one, and then they'll say, draw the SN mechanism with this molecule, with this halalkane. Any other questions?
What's the definition of a nucleophile again?
Nucleophile is something that loves a nucleus. So basically tends to be something that is neutral or negatively charged and has a pair of electrons. You can think of nucleophiles like ligands. It's a very similar definition. It's just because you're using it in different areas of chemistry, they've just been given different names. But it's the same thing. Any other last minute questions?
No.
Okay, cool. In terms of slides and notes, you will get all the slides, you will get all the notes, that's fine. The only thing that I ask in return is that you fill out our survey. Survey will literally take you 5-10 minutes. We just want to know what you thought of the workshop. Basically, if it's a helpful way of teaching or if it's just quite inconvenient because I can't actually talk to any of you. It is very weird to monologue for over an hour. I will send you an email with the survey now, actually, after this, because we can send it through Crowdcast. Fill it in as soon as possible, and basically as soon as you fill it in, I will start sending out the presentation to those of you who have filled in the survey. I'll do that tomorrow though, because I would quite like to get home.
No.
But anyway, any last minute organic high level tips? Practice, practice, practice. You have to practice your mechanisms over and over again. Teach it to your friends. It is fun, so don't be too bored by it. Yeah, that's all from me. Good. Come to biology next week. But I'm going to go home because I'm done. Have a lovely evening. Thank you for coming. It's so nice to have all you. Wow, we've still got 130 people connected. That's amazing. Physics will be posted soon, but it's basically, I think it's in about a month's time, but we'll post it all on our website and we'll send you emails. And maths will be in a couple of weeks as well. Again, we'll post it and we'll keep you updated. Cool. That's all from me. Have a lovely evening and bye from Lantana.
Bye.